All right, welcome everyone to another deep dive. Today we're going to be tackling a presentation by Somaya Abbas Bergomi, and I think this one's going to be really interesting.
Oh, yeah.
Yeah, it looks at kind of the intersection of optics, ceramics, glass, even things like solar cell technology.
Wow.
So it's really all over the place.
Yeah.
But we're going to try and pull out, I think, the most important scientific takeaways, the ones that have the broadest application. So
Sounds good.
stick with us. What's interesting about this presentation, I think, is how it tries to pull together these different areas of material science.
Yeah, you're right. I mean, you don't usually see optics, ceramics, and solar cells all in one presentation.
No, and it kind of goes from the very small microelectronics kind of level all the way up to, these larger applications, energy solutions.
Right.
So there's a lot here. And what we're going to try and do is really distill it down to, the essential knowledge for, anyone who's listening, whether you're a student or a researcher or just someone who's curious about the latest advancements in science and tech.
Awesome.
So shall we jump into it?
Let's do it.
All right. So the first topic that we're going to tackle is something called microelectronics, packaging by metal nanoparticle pastes.
Okay.
Now, this sounds very, very small, but the implications are huge.
For sure. And as the presentation points out, conductive pastes in general are just absolutely essential to electronics manufacturing.
Yeah.
I mean, they form the conductive circuits, they make electrodes, resistors, even dielectrics, so they're absolutely vital components.
Yeah, now the traditional way that this is done is through what are called thick film pastes, and these are essentially mixtures of metal powders. Now these are relatively large, we're talking micrometer to submicrometer size, with organic compounds. So think of it like, fairly large metallic grains in a kind of binder.
Yeah, exactly. And then the way these pastes are processed is by first applying them to a substrate. And this is usually something like a glass or a ceramic. They use techniques like screen printing or dispensing, for example. And then the next step is to dry the paste. But then, and this is where it gets tricky, you have to fire these pastes at really high temperatures, often exceeding 550 degrees Celsius.
Wow.
And this is to basically burn away the organic compounds
Yeah.
and also to fuse those metal particles into a conductive film.
So that high temperature firing, I mean, that sounds like a major limitation, right?
Oh, absolutely. It is. It basically restricts you to only using substrates, like I said, glass and ceramics, that can withstand those really high temperatures. So that's a key driver behind why this new technology, metal nanoparticle paste, is so exciting.
Okay.
And here we're talking about metal particles that are just a few to maybe a few dozen nanometers in size, so much, much smaller than those found in thick film pastes. And this really opens up the possibility of, miniaturization,
Right.
much smaller electronics, also flexible electronics, things like that.
Okay, so we're talking about incredibly tiny particles that have the potential to really revolutionize things. But, the presentation mentions they're not very stable on their own. What's the challenge there?
Well, it's really a matter of surface area. When you go down to the nanoscale,
Mm.
these particles have this enormous surface area compared to their volume. Think about, crushing a sugar cube into powdered sugar. The total surface area just skyrockets.
Oh, okay.
And this increase in surface area, it leads to a much higher surface energy. So the nanoparticles they're much more reactive, and they want to clump together. And this is really what those organic coatings are there to prevent.
Got it.
They're like little guardians,
Hmm.
keeping those nanoparticles from basically glomming onto each other and becoming unusable. And the presentation even mentions, gas evaporation is one of the methods that's used to prepare these things.
So there's a lot of control that has to go into making these things, it sounds like.
Definitely.
And the presentation highlights specifically monodispersed gold nanoparticles. And it mentions a diameter of less than 10 nanometers.
Yeah.
So why gold? And what's the significance of them being so small and monodispersed?
Well, gold is chosen, often because it's an excellent electrical conductor,
Mm-hmm.
and it's also very resistant to oxidation. So it doesn't react with air and lose its conductive properties. Now, dispersed basically means that the nanoparticles are all very uniform in size.
Okay.
So it's like having a batch of perfectly identical tiny little spheres.
Yeah.
And this uniformity is really important to get consistent performance in those conductive pastes.
I see.
And then the sub 10 nanometer size, that's also crucial because it allows for good dispersion, meaning basically that the nanoparticles spread out evenly within the paste. Think about trying to spread out, large pebbles versus fine sand.
Oh, okay.
The finer particles are going to distribute much more uniformly, And it's essential for creating a smooth and, consistently conductive film.
So we have these tiny, uniformly sized, coated gold particles all in a paste. How do we go from that to actually creating a circuit pattern? And especially if we're talking about using these on a flexible plastic base, we can't use those really high temperatures.
Right, and this is where something really interesting comes in. It's called the quantum size effect. So because these nanoparticles are so incredibly small, their properties actually start to deviate from those of bulk metals.
Oh, okay.
And one of those altered properties is the temperature at which those organic protecting groups and the other organic components in the paste will actually decompose and basically vaporize.
Oh, interesting.
So you can actually remove them and fuse those metal nanoparticles together into a conductive film at temperatures below 300 degrees Celsius, which is a huge difference from that over 550 degrees Celsius that we're talking about for those traditional thick film pastes.
Okay, so that lower temperature, I mean, that really opens up a whole world of possibility. Suddenly you can use these pastes on plastic substrates. And now we're talking flexible displays, bendable electronics, wearable technology, right?
Absolutely. So it greatly expands your range of materials and opens up these whole new design possibilities for flexible, even stretchable electronic devices.
Right.
And also because the nanoparticles are so small, you can achieve much finer circuit patterns. The presentation mentions being able to get lines in spaces less than 50 micrometers using screen printing,
Wow.
which is, a big jump in resolution compared to what you could achieve with those traditional pastes.
And they're anticipating even being able to get down to 10 micrometer lines.
Right.
I mean, that's just amazing, the level of miniaturization. Plus, the fact that they're also, they're using this superior dispersion of these nanoparticles for inkjet printing as well. So even more precise, I guess, in terms of creating these tiny patterns.
Exactly. So inkjet printing gives you even finer control over where that conductive material gets deposited, allowing you to create more intricate, more higher resolution circuit designs.
Oh.
And actually, it's not just circuits. The presentation even touches on using metal nanoparticles as joining materials. So kind of like a high-precision, low-temperature soldering, if you will, for connecting tiny components.
So we've gone from, relatively large metal powders that need a ton of heat to these incredibly small nanoparticles that let you use lower temperatures, they give you much finer detail, and they open up this whole world of flexible electronics. I mean, that's a pretty big leap, right?
Definitely, yeah. I mean, it really highlights the potential of working at the nanoscale.
Yeah.
This opens up so many new possibilities.
Okay. So let's shift gears a little bit now. The presentation also looks at the application of Raman scattering in chemical analysis. And this seems like a completely different area.
It is. But it's another fascinating example of how light can interact with materials to give us really valuable information. And specifically, the presentation mentions that the intensity of Raman scattering in semiconductors can be enhanced through this interaction with surface plasmon resonance.
Okay, so let's break that down a bit. First of all, what is Raman scattering, and who is this Sir Raman guy who discovered it?
Well, Sir C.V. Raman was an Indian physicist.
Okay.
And he discovered this phenomenon, which is basically the inelastic scattering of photons by molecules. So when light hits a molecule, most of it scatters elastically. And this is called Rayleigh scattering. And this just means that the outgoing photons have the same energy as the incoming ones, kind of like a perfectly elastic collision.
Okay, so the light just bounces off without any change in energy.
Right. But a very small fraction of those scattered photons undergo what we call Raman scattering. And in this case, they either gain or lose a very small amount of energy during their interaction with the molecule. And this energy change, it corresponds to changes in the vibrational or rotational energy levels of that molecule.
So the scattered photon comes away with a slightly more or slightly less energy than it started with.
Yeah. And this is all based on basically how it interacted with the molecule.
Exactly.
And the presentation specifically mentions the transitional Raman effect as being important to chemists. Why is that?
Well, that tiny energy difference between the incoming and outgoing photons, that is unique to each molecule and to the particular energy transitions that it undergoes. So it's kind of like a unique fingerprint for each molecule.
Oh.
And so by analyzing that spectrum, basically the distribution of those inelastically scattered photons, chemists can actually identify the molecules that are present in a sample and even get some clues about their structure and their bonding.
So you shine a light on a substance, You analyze the very slight change in color of the scattered light, and then you can figure out what that substance is made of.
Yep.
That's pretty amazing.
That's pretty powerful. And like you mentioned earlier, that effect can actually be enhanced through this interaction with surface plasmons and semiconductors.
Right. Okay. Now, what exactly are surface plasmons? Well, think of them as these collective oscillations of electrons that happen at the interface between two materials. One that has a negative dielectric constant, which is usually a metal, and one with a positive dielectric constant, which could be a semiconductor, or even just air. So it's kind of like a wave of electrons rippling across that surface.
Oh, okay.
And when light hits that interface at a specific frequency, it can actually excite those oscillations. And this creates a really strong electromagnetic field that's concentrated right at that surface. And this enhanced electromagnetic field can then dramatically amplify the intensity of the Raman scattering from any molecules that are close to that surface.
So it's like you're using a much stronger light source
Yeah.
focused on this tiny little area, and that gives you a much clearer signal of what's there.
Exactly. So it's like a built-in amplifier for your signal.
Oh, I see. Now, the presentation also mentions glass and silicon solar cells,
Right.
and it doesn't go into a whole lot of detail, but they're kind of mentioned as part of the overall picture.
Right. I think given, you know, how many topics this presentation covers, the fact that glass and silicon solar cells are even mentioned probably just reflects Abascomi's broader expertise. I mean, obviously glass is this fundamental material in optics and electronics. It's used as a protective and structural component in solar cells. And silicon solar cells, of course, are very well established, widely used technology for converting sunlight directly into electricity.
Right.
And so even though the presentation doesn't really go into the specifics, the engineering details or the material science behind those things, their very mention, I think, underscores this interconnectedness of the topics that we've been discussing, from the fundamental properties of materials like glass and silicon, all the way to these principles of light interaction that are so central to both Raman scattering and solar energy conversion.
It gives you a sense of the kind of research that she does, right?
Yeah.
She's really kind of bridging all these different scientific domains. All right, so we've covered a lot of ground today, from, these really intricate nanoparticle pastes to this powerful analytical technique, Raman scattering, and even, touched a little bit on the well-established field of silicon solar cells. What, for you, are the kind of key takeaway messages?
I think the central theme for me is the power of manipulating materials at this very fundamental level. It's really driving innovation in all these areas. So, with those nanoparticle pastes, it's all about controlling the size and properties of materials down at the nanoscale, which lets you overcome the limitations of those traditional technologies.
Yeah.
And with Raman scattering, it's about understanding and leveraging those subtle interactions between light and molecules to really gain these deep insights into, the composition and structure of matter. And I think that brief mention of the glass and silicon solar cells, that reminds us of the importance of material science in general for tackling these big global challenges like clean energy.
Yeah, and they're not just, these sort of abstract concepts. I mean, we're talking about concrete implications for how we manufacture electronics, how we analyze the world around us, and how we harness energy. It's all kind of interconnected in these amazing ways.
Oh, sure.
So as we wrap up this deep dive, I want to leave you with a final thought. Considering how quickly nanotechnology and photonics are advancing, what totally new materials or analytical techniques might emerge in the next few years, and how might those breakthroughs change things like microelectronics, chemical research, and renewable energy in ways that we can't even imagine yet? Just something to think about as you go about your day. Thanks for joining us.